All right, so let's get right into it because we've all been there. You're holding an ice cube, maybe for a drink, maybe for an injury, and after a minute, that nice, soothing, cold sensation just changes. All of a sudden, it's this sharp, stinging pain that feels weirdly like it's hot. Today, we're going to figure out exactly why that happens. I mean, it's such a strange experience, isn't it? Cold is supposed to be the literal opposite of hot. But when you hold onto ice for too long, that pain you feel is so much like a burn. So what's going on? Is your brain just getting confused, or is there something deeper happening here?
So let's start by digging into what we're calling the cold burn paradox. Because the fact that extreme cold and extreme heat can feel almost identical, well, that's not just your imagination. It's a very real and very fascinating feature of how your body is wired.
And this really gets to the core of it. Your skin's physical reaction to something intensely cold is almost exactly the same as its reaction to something intensely hot. The signals that get sent to your brain aren't just getting crossed, they're basically screaming down the same danger highway, which makes it really hard for your brain to tell them apart. Okay, so to really understand why this confusion happens, we need to look at the specialized hardware that's embedded in your skin. This is all about your body's built-in, non-stop alarm system. And that brings us to the star of the show, nociceptors. Now, these are not your everyday nerve endings that just sense a light touch or a change in temperature. Nope. Their only job is to shout danger when they detect anything that could potentially cause damage to your body's tissues. They are your emergency responders. And here's the crucial part. Your nociceptors are, well, a bit of a generalist. They don't have separate, color-coded alarms for different kinds of threats. Whether it's a sharp object, a hot stove, or a piece of dry ice, it all trips the exact same wire. And that's why the sensation of extreme cold gets lumped in with the feeling of a burn.
Now, what's wild is that the way the damage happens is totally different. Extreme heat basically unravels and breaks apart the proteins that make up your cells, but extreme cold, it causes the water inside your cells to freeze, expand, and then burst the cell from the inside out. But to your nociceptors, damage is damage, and they fire off the same urgent warning signal for both.
All right, so we've got the biology down. Now let's switch gears and look at the chemistry that can create this kind of intense cold, like almost instantly. How do you actually make something cold on purpose? The answer lies in something called an endothermic reaction. And the name pretty much says it all, right? Endo means into, and therm means heat. It's a process that literally pulls heat into itself from everything around it. And when you suck all the heat out of the environment, well, the environment gets really, really cold. And, this isn't some rare high-tech lab thing. These reactions are happening all around you all the time. Just melting an ice cube in your drink is endothermic. It has to pull heat from your soda to turn into water. Even cooking an egg is endothermic. It needs heat to go into it to change its whole structure. But some endothermic reactions are way more dramatic. Let's look at one of the absolute classic examples. A reaction that gets so cold, so fast, it can literally freeze water on contact. It's almost crazy how simple it is. You just take two white powders that look pretty ordinary, barium hydroxide and ammonium thiocyanate. You stir them together in a beaker, and almost instantly, these two solids turn into a slushy, goopy liquid. But as that's happening, something incredible is going on. The temperature just plummets down to a shocking -20 degrees Celsius and sometimes even colder. That's colder than the freezer in your kitchen. It gets so cold so quickly that if you do this on a wet block of wood, the beaker will freeze itself right to the surface in just a minute or two. So how? How is that even possible? Most reactions that get this cold need a ton of energy pumped into them to even happen, but this one just goes. Well, the secret isn't about heat energy. It's about chaos. This whole reaction is powered by a massive, sudden explosion of disorder. And that leads us to this little piece of scientific magic, the Gibbs free energy equation. This simple-looking formula is really the key to understanding how a chemical reaction can suck up a ton of heat from its surroundings and still happen all on its own, spontaneously. Okay, so let's break it down real quick. The first part, that delta H, is called enthalpy. You can just think of it as the change in heat. Since our reaction is endothermic, it absorbs heat, this number is positive. And usually, a positive delta H means a reaction won't just happen on its own. But then, you have delta S, and that's entropy, which is just a fancy word for disorder or randomness. See, in our reaction, we start with two very neat, orderly solids.
But when they react, they explode into a messy liquid, ammonia gas, and water. The whole system becomes way more chaotic, so the change in entropy is huge and positive. And this, right here, is the kicker. That powerful drive towards more and more disorder, that massive increase in entropy, is so strong that it just steamrolls the reaction's need for heat. It becomes the engine that forces the whole thing forward. And to do that, it has to steal the energy it needs from its surroundings, which is what causes that incredible drop in temperature.
Okay, so let's tie this all together. We have the biology of our danger receptors on one side and the chemistry of instant cold on the other. How do they connect to create that feeling of a cold burn?
You know, this quote really sums it up perfectly. At the end of the day, your brain is a survival machine. It doesn't really care about the precise scientific reason for a threat, it just cares about getting you to react, and fast. Pain is a fantastic motivator.
And this just lays it all out, step by step. Some process, whether it's a crazy chemical reaction or just holding on to ice too long, creates extreme cold. That cold threatens to damage your cells by freezing them solid. Your nociceptors sense this threat and fire off that urgent general-purpose danger signal. And your brain, getting this intense alarm bell, scrambles to put a label on it, and it uses a familiar urgent one, burn. So really, it all comes down to brilliant efficiency. Your body's warning system has one main goal: keep you alive and in one piece. And to do that, it uses one incredibly effective, high-priority alarm for any big thermal threat, whether that threat is coming from a blazing fire or a freezing frost.
And that leaves you with a really fascinating question to think about, right? This whole thing is a powerful reminder that what we actually perceive isn't a perfect, high-definition picture of reality. Our senses are constantly interpreting, simplifying, and giving us shortcuts to help us survive. So you have to wonder, what other shortcuts are they taking?